So thank you so much for inviting me to lecture to this great audience. I don't think I'll ever have a better audience to give a lecture to. And thanks for mentioning Fruit Pixel. He was my favorite economist when I was a PhD student, not only because he tried to integrate kind of micro and macro, but he tried to put a concept of time into economics with some mathematics. And what I'm going to talk about today is a paper that I wrote for this conference called Adverse Selection and Liquidity from Theory to Practice. And it's going to try to put time into a concept of liquidity, as well as do some other things which connect my past research to research I'm doing now. We will finish, since this is a symposium on money and banking, I'll finish talking about money and banking by relating what we're talking about to trading and funding liquidity. Actually, I wrote this paper with Anna Vijayeva, my co-author, who's probably here somewhere, and we are happy to be able to put this together. So, adverse selection and liquidity. The topic raises a bunch of questions. Is there a simple way to measure liquidity? This has been a problem, I think, for researchers in liquidity over the years, with measuring it. And how can theoretical parameters like lambda, which is a price impact parameter from my 85 paper, how can that be implemented empirically? There have been lots of different empirical implementations over the years, and they give widely different results. And how can empirical measures of liquidity be connected through adverse selection to the properties of prices? These are all kind of fundamental questions related to liquidity, and we're going to try to tie these together today. So what's the answer? The answer is I'm going to use some very general principles to derive a formula for liquidity that I call L. And you'll see that it has a cube root in it, that is the ratio of dollar volume to returns variance scaled with a constant to make it dimensionless. So it's a measure of liquidity. The higher value of L means more liquidity. The reciprocal, you can think of 1 over L as illiquidity. And illiquidity is a measure of transactions costs. So illiquidity might be 1% or it might be 40 basis points. And it's going to have a nice interpretation as 40 basis points, say, being a transactions cost. And what I'm going to do in the paper is I'm going to map this liquidity measure L into some of my past research, in particular the price impact parameter lambda, and a new price impact parameter that I'm going to call kappa that has time units in it and takes account of the speed, essentially, with which you can trade. And then I'm going to show that when you connect this liquidity parameter to theoretical models, that you can actually talk about things like the informativeness of prices and the resiliency of prices that are kind of important, I think, for thinking about market efficiency. Okay, I've got lots of slides here, so I'm not going to get through all of them in 25 minutes, so I'll probably skip some as I go along, but certainly not this one. So let's think about noise trading in one-period models. There's a long tradition of thinking about noise trading and a long tradition of thinking about one-period models. And one paper that I like to use is, in some ways, a kind of straw man is Grossman and Miller's 1998 paper, where you have essentially competitive traders demanding liquidity as noise traders by dumping a quantity in the market, and then you have competitive market makers supplying liquidity by taking the other side of these quantities that are dumped into the market. And one of the fundamental assumptions behind that, I think, is the ideology from the 1970s, and that is that financial markets are perfectly competitive. And so this Grossman and Miller modeling approach is consistent with the idea that financial markets are perfectly competitive. In '85, I wrote my paper, Continuous Options and Insider Trading, that broke with this tradition. It was really, when I was working on this paper in the 1980s, it was really hard to find anybody who thought that financial markets were not perfectly competitive. And the idea in that paper is that a large trader with a private signal that gives him monopoly power over some information goes into the market to trade on it, but he moves the price as he trades. And so he has market impact, and because he knows he has market impact, he will kind of scale back the quantity he trades, just like a textbook monopolist would as a supplier of a product. And he does that essentially to reduce price impact. And growing up, this was pretty obvious to me because my father was a cotton merchant who was a big trader in the cotton markets, and he would come home at dinner and complain about how illiquid the market was and how he couldn't trade everything he wanted to trade. So this paper has a feature in it called a market order model. So rather than submitting a demand schedule, the trader announces a quantity to the market. And the market then supplies liquidity to this trader. And I think of this as kind of capturing some features of the way organized exchanges function back in the 1980s. And in the paper, I talk about this in a bit more detail. But the idea being that not being able to condition on prices means someone else has some flexibility that you don't have. And then another paper that's relevant to this discussion is my 1989 paper. In that paper, traders still exercise monopoly power, but they submit demand schedules. It's like a Walrasian equilibrium in that demand schedules that are functions of price are submitted to kind of an auctioneer, and the auctioneer calculates a market clearing price. But each trader, when they submit their schedule, they take into account that they're going to affect the price, and that affects the schedule that they submit. And I think that this way of trading approximates what you see now. So whereas my 85 paper was approximating kind of what took place on the floor of the Chicago Board of Trade, where I was working as a PhD student when I was writing my dissertation, this 1989 model was looking to a kind of way markets should work, which is closer to the way markets work to now, where we have fragmented exchanges, but at any rate, traders can submit price contingent schedules. Still exercising monopoly power, though, over their private information. So I've been working on these questions since the 1980s, and I'm still working on them today, even in one-period models. For example, I have a couple of papers with Zhongmin Li, a former PhD student at the University of Maryland, who's now at Washington University in St. Louis. And what we've done is used a symmetric setup, kind of like Diamond Verrecchia's nice 1982 paper. I'm just beginning to appreciate some of the nice things in that paper. But what we show is that with imperfect competition, rather surprisingly, the prices that come out of the auction process are, because of the symmetry assumption, exactly the same as the prices that come out of competitive trading. So you can't look at prices and kind of decide whether the market is competitive or not competitive. Instead, imperfect competition shows up, as you maybe should have expected, as quantities being smaller. And if there's not enough demand for liquidity, you might not have any liquidity at all, and the quantities might go to zero, in which case you have something similar to what Grossman and Stiglitz were talking about in 1980, when they were taking limits as noise trading vanishes. And what we show in one of these papers is that when you take that limit, you still wind up with a market that's imperfectly competitive, and indeed infinitely imperfectly competitive. Okay, so let me go to forward a step. Instead of talking about one-period models, let's talk about dynamic models. So essentially, I want to talk about time and liquidity. Obviously, to talk about time and liquidity, you need to connect. You can't use a one-period model unless you have some really good intuition about what a one-period model implies for time. So in my 1985 paper, there's a one-period model, and then there also is a dynamic model and a continuous time model. And the large trader in the dynamic model or the continuous time model, who has this private information, winds up trading gradually over time. So rather than suddenly incorporating all of his information into prices as quickly as possible, he walks up a supply schedule, but he walks up the supply schedule relatively slowly. But I have noise traders in that paper, and the noise traders in that paper essentially trade instantaneously in exogenous quantity, and that's as if they were perfect competitors demanding liquidity, like in Grossman and Miller's model. If they could in that paper, it's not in the paper, but if you model them as wanting to control their transactions costs, they wouldn't demand liquidity instantaneously. They would demand liquidity slowly and slowly could mean over 5 minutes. It doesn't mean very slowly. They just need to smooth out their trading a little bit, and they could cut their transactions costs a lot. In that paper, they assume not to do it. One way to change the environment so that they do it is to, instead of make them exogenous noise traders, give them an endowment shock and let them hedge the endowment shock by endogenously choosing how fast they want to trade. If you have a model that just does that, you get something that's related to Grossman and Miller, but it winds up being something very similar to Dimitri Vaina's 1999 paper, where traders actually are trading gradually. And recently, Anna Vijayeva and Yajin Wang and I have a paper where traders are trading on private information in a model that's kind of a stationary setting. And what we do there is we assume all the traders have private information. Everybody trades on their private information and wants to incorporate it into prices. These models need some mechanism for generating trade. There's noise trading, there's endowment shocks that I've already mentioned. This one uses overconfidence. You can also use private values. And the idea behind overconfidence is all the traders think that their signals are better than the other traders' signals, so they all kind of want to trade in favor of their own signals and against everybody else's signals. When you do that, you get a nice, clean equilibrium model of trading in which you don't have to, except for this overconfidence assumption, you don't have to make any controversial assumptions. The market is constantly clearing, prices are constantly reflecting information, and the equilibrium has every trader trading slowly. Essentially, the time derivative of their inventories exists because they're trading small amounts at each period of time. And the way the market clearing mechanism works is that there's an auction being held essentially continuously for derivatives of inventories. So I think this paper actually solves some of the problems that my 85 paper was kind of halfway solving. It adds a monopoly power, but then it makes everyone respond to price impact incentives. Behind it, there's this interesting intuition that instantaneous liquidity vanishes. In my 85 paper, you can kind of trade a large quantity very quickly, and you'll move the price somewhat, but you won't move the price an infinite amount. In this 2018 paper, you cannot trade a large quantity very quickly. If you try to do that, you'll move the price an enormous amount. So we need a different parameter. Instead of using lambda, which is the price impact in the 85 paper, we use something we call kappa along with lambda, which is a price impact parameter that takes into account the rate of trading. We've got another paper, I'm not going to talk about it today, on stock market crashes, where essentially the stock market crash of the flash crash of 2010 kind of can be explained this way as a large trader not demanding too much liquidity, but demanding it too quickly. They were trading a large quantity, but they should have traded it more slowly perhaps to lead to less price impact. Another feature of this paper is that prices reveal information immediately, and anomalies are going to vanish when the market is extremely illiquid. So if you look at the market and you think that Fama's concept of market efficiency holds, you should not infer from that that markets are competitive. You should infer from that that markets are imperfectly competitive. In a competitive market, actually, you get anomalies related to a Keynesian beauty contest. Is one of the features of this paper. In carrying it further and turning this into a kind of practical proposal, Zhongmin Li and I have a paper where we propose essentially a market clearing mechanism that clears and flows rather than stocks, so that you trade by saying I want to buy 1 share per second, something like that, for several hours if I want to buy thousands of shares. We think that that is a better solution to the problems of high-frequency trading than the proposal by British Crampton and Shum, which is called frequent batch auctions. You can read the paper and find out more about that. Okay, so what I want to talk about for the rest of the time is market microstructure invariance. And I think I've got about 15 minutes, is that right?
You got 12 minutes.
12 minutes, okay, so I'm going to run out of time, but because I'm on slide 4. So the basic, but that's fine, the rest of these slides you can read. So the basic idea of invariance is that there are parameters in markets that can be divided into different categories. There's some things that are easy to observe. Think about it if you're an empiricist. There's some parameters that are easy to observe. There's trading volume, there's the market price, there's returns variance or volatility. So those are things that if we can't observe them directly, we can estimate them with reasonable accuracy. And then there are other parameters that are harder to estimate. And those hard to estimate parameters fall into 2 categories. This is kind of the key to understanding what we do. One category is parameters that vary like crazy across assets. They may vary by a factor of 10 or a factor of 100. We're talking orders of magnitude here. Like trading volume, which is observable, but things that are not observable, like the number of bets that arrive per day or the size of bets that arrive. So the basic idea here is that markets function with large traders placing bets, and they endogenously decide the size of the bet that they want to place. You can think of a bet as a meta order or a decision to trade a rather large institutional quantity. So what we're looking for is a universal price impact formula, or a universal formula for describing liquidity that is applicable across many different markets simultaneously. And so that's what we're going to try to do here. And there are a whole bunch of different ways of doing this, but they all are based on something that we call market microstructure invariance. And the key idea behind market microstructure invariance is let's take these parameters that are hard to observe, divide them into the categories of ones that vary like crazy across assets, and parameters that are relatively constant across assets, maybe perfectly constant, but we think constant across assets. And then maybe using a special data set, you could estimate or calibrate these constants because these constants are the same across assets. So if you have, say, 7,000 ticker symbols in the market, you don't need 7,000 models of market liquidity. You just need one model and a few calibrated constants. So let me describe how we do this. We have a bunch of notation here just for basically to make the point that units of measurement are going to be very important. This has kind of the flavor of physics where you have to look at it very, very carefully. I'm going to skip the notation slide and explain to you what it means later, but we have three things: price, volume, and volatility that are easy to observe. We have the sizes of bets, the number of bets, the horizon over which they're executed, the price changes that they imply, their execution implies, and things like accuracy and error of prices that vary greatly across assets. And then we have some moment ratios and other parameters that we think don't vary across assets, but the key one is the C, which we think is about $2,000. And that represents, you can think of as the cost of the information or the cost of the signal that allows you to place an informed bet. And the big, bold hypothesis here is that that's constant along with some other things, but mainly it's that one that's constant. So we're going to generalize my 85 paper. In my 85 paper, you have a price impact parameter lambda. You multiply that by Q, and you get price impact that we call delta P. You could essentially divide that by P, and then you get price impact that we call capital G as a fraction of the value that you've traded. And of course, that price impact is going to be a function of how much you trade. And in that particular paper, price impact is linear. So lambda shows up as a linear coefficient multiplying, or as a coefficient multiplying Q. So it's a linear function. So we're going to generalize that. And what we're going to try to do is we're going to try to write down a very simplistic model that's specified in terms of a very small number of equations. That's not really a model, but what we would call a meta model. That's some equations that we would think a model should satisfy. So we wrote down three equations. One is just a definition of volume that says volume is the number of bets times their average size. The idea that trading makes prices move. A lot of people think information makes prices move. We don't think so. We think most price movements are the result of trading. And so that says that the returns variance is that you see in prices is the sum of the price impact of all the bets that are arriving at rate gamma and have a contribution to variance that's the expected value of delta P squared over P. And then we have that contribution to variance is equal to the price impact of the bet. We've departed from the linearity assumption by putting an exponent of beta on Q. It should be absolute value of Q up there in the front line. So we have three easy to measure quantities, but five hard to measure quantities. We would like to solve this little three equation model for the hard to measure quantities in terms of sort of easy to measurements, but unfortunately, it's three equations and five unknowns, so we need two more degrees of freedom to fill in. And the way we do it is we add some extra equations. So we're going to add this invariance equation that says that the market impact cost of a bet is constant. The dollar market impact cost of a bet is a constant dollar amount. It doesn't vary across markets. Ultimately, through theory, it's related to the idea that the cost of information is constant. And when we add that assumption, we get four equations. But now we've got, it turns out we've actually added another unknown, which is a funny moment of Q. So we have four equations and six unknowns. So we haven't really appeared to make our problem any easier to solve. The way to make it easier to solve is to assume that the distribution of Q is the same, which are sizes of bets, is the same across markets except for a scaling parameter. And the scaling parameter is going to show up in the mean, but the other moments then would be constant. And that gives us some moment ratios that we can assume to be constant. They give us two other equations. And now we have six equations and six unknowns. And we can solve for the difficult to measure things in terms of the easier to measure things and in terms of these constants, the cost of a bet and moment ratios that we're assuming to be invariant. And let me show you what the solution is. The solution can be expressed in terms of this liquidity measure L that I advertised at the beginning of this talk. And it turns out that you can define 1 over L, this is the reciprocal of how I defined L earlier, as this ratio, sigma squared c in the numerator divided by m squared PV in the denominator. You take the cube root of it. And this 1 over L is a dimensionless number because the numerator and the denominator are both measured in terms of dollars per unit of time. And this measure turns out to be the volume-weighted average cost of a bet. And in terms of that 1 over L, you can actually solve the system of equations. If we go back and look at these equations, they don't look like linear equations, but if you take logs of all of the equations, it's a nice simple linear equation system, and it has a nice simple closed form solution. And in terms of the closed form solution, you get that the dollar size of a bet is just a constant multiple of L. So it's going to vary across markets as liquidity market varies with bigger bets and more liquid markets. This number of bets that arrive, or the rate at which bets arrive, gamma, also varies across markets, essentially proportional now with L squared, so more bets and more liquid markets. And the price impact of a bet can be expressed as a very simple formula that's 1 over L. It's kind of an illiquidity measure that's measuring price impact, times a constant, and then times a power of Z, which, if you map it into my 85 paper, is linear price impact. And what's Z? Z is just a scaled way of measuring the size of a bet as a multiple of mean bet size. So a lot falls out from these very simple equations. And if you assume that you know the value of these hard-to-observe moments, you can make predictions about kind of any market you want to. You get empirical predictions kind of for free from this. I'm going to show you a couple of pictures out of a recent paper with Anna Vijayeva. If you think that this C being constant is controversial, what it implies is if you looked at the sizes of bets, they would vary with an exponent that's minus 2/3 as a function of our measure of trading activity. She has a large data set of portfolio transitions, which we think of as institutional bets. And the red line you're looking at is a line with a slope of minus 2/3. And you can see that bets as the size of average daily volume are much bigger in less liquid stocks, or stocks with low levels of volume. Bets as a fraction of trading volume in a stock like Apple that has very high trading volume or very small fraction of trading volume. Okay, similarly, the distribution of the bet sizes turns out, theory doesn't say it, but it looks like a log normal, consistent with the idea that the shape is a constant. And you can think about, when you think about transactions cost, you get this puzzle that we have a paper on. The puzzle is that the square root model of price impact seems to be a lot more accurate than the linear model. Okay, so there's another approach that we call dimensional analysis that allows, like physics, the way it's done in physics, it gives you the same results, so I'm going to skip it. And the question then is, where is the adverse selection? How does this connect to my 85 paper? How much time do I have?
2 minutes.
2 minutes. So the answer is, it connects to Trainer's model, which I think is a wonderful model. But I'll talk about how it connects to my 85 paper, and then make a concluding comment. In my 85 paper, I've got a little solution to the one-period model here, and then show with some equations that you can map that solution into the meta model that I just showed you. And essentially, there's a perfect mapping. And the result of that perfect mapping is that the parameters in the 85 paper that are kind of hard to pin down empirically, get pinned down exactly empirically through this mapping. But underlying it is the idea that the cost of the signal is constant, and that this constant cost is, since it's unchanging across markets, it gives all markets kind of common features. So let me fast forward to the end. We've got this research on smooth trading that I talked about earlier. Essentially, if I skip forward a few slides, I can map the size of a bet into what the bet looks like if you trade gradually, what market impact looks like if it occurs as a function of time rather than just the size traded. And this mapping, again, is kind of perfect mapping into the model. It winds up connecting the size of bets and their price impact to parameters that measure the informativeness of signals, and so it connects adverse selection directly with this meta model. It didn't have any adverse selection in it. One of the funny things about the meta model was there was no adverse selection, but here we get some adverse selection in the meta model. So let me skip to the last slide and talk about trading and funding, liquidity, and time, because this is a conference on banking. So we think that trading liquidity and funding liquidity are the same thing. And we have kind of two measures of liquidity, L, which is kind of measured in basis points, but something else called gamma, which is measured at kind of the speed with which bets arrive into the market. And we think that if you're thinking about margins or repo haircuts or bank capital or bank equity issuance, most people think about the riskiness of this as being measured by standard deviation. But we think that's wrong. The right way to measure the riskiness of, let's say, a haircut on a repo is to take into account not only the standard deviation, which you see over here on the right-hand side in the denominator, but also take into account the speed with which defaulted collateral would be liquidated if the repo kind of collapsed. And if the speed is very slow, it kind of makes it riskier. And when you take that speed into account to measure how risky it is, you wind up with 1 over L as being proportional to your haircut, not the standard deviation signal. And so we think this is a way of thinking about funding liquidity that connects it exactly with trading liquidity. 1 over L measures illiquidity both for trading and for funding. And what makes a bank is that its assets are very illiquid. So it's so illiquid as a practical matter, you can't liquidate them. And so you wind up trying to get the bank to raise capital if it's underfunded. And when you do, the equity issuance takes time. You plug this into the adverse selection model I just talked about and put in some reasonable parameters, and it may take several months for the bank to raise capital. In contrast, government securities have high volumes and can be traded very quickly. That's why people like to trade them, and that's why they're associated with liquidity. You can also use gamma and sigma, as I mentioned earlier, to explain stock market crashes. So conclusion, and I'll stop, is that this meta model implies a liquidity measure that we call capital L that maps back to my 85 paper and to the generalization of my 89 paper that's the smooth trading model today. It's consistent with a kind of model of block trading where traders go in and trade huge chunks immediately. It's also consistent with the order trading model where they trade smoothly over time. It generates a lot of very useful empirical implications from this invariance assumption. And by connecting liquidity and time, it has a present approach for setting bank capital. It's supposed to be an L there, and deals with some problems of banking that I think are going to be the rest of the conference.